Hello, everyone. Thank you for coming today. Today it's actually our third webinar, but it's the second part of our series on reporting survey and questionnaire studies. And as promised last time, today we're going to focus on scholarly and useful reporting of quantitative results. My name is Matheus Andrade. I'm an associate professor at the UCL Center for Engineering Education. I serve as deputy editor in the EJEE, but you should and absolutely can call me Matt. So for today, I have a very quick outline because today we're doing things slightly differently. Today we're having a 1 hour webinar. So it's going to be quick fire, and I hope to pack in as much of a punch as I can in 1 hour, whilst also making the content digestible. Of course, you're going to be able to see this recording afterwards on YouTube, on the SEFI channel, so do make sure that you refer to it in the end. Today, we're going to look at three important things, and that's my promise of what we're going to cover today. First is identifying and reporting type 1 and type 2 errors accurately, appropriately, to interpret and present confidence intervals and effect sizes, and justify sample sizes via power analysis. I do recognize that there's a bit of jargon in there, but this is just to give you a little bit of the words that you would read in a book or that you would see in a paper referring to the contents that we're going to talk about today. So, as Christina mentioned, I am a mathematics educator. I've been teaching mathematics for more than 12 years now. And often when I talk about mathematics, people might make a face like you see of the confused lady in the little picture to the right. And when we talk about mathematics or statistics or anything quantitative, we think always of the possibility of error, right? Maybe there is a problem in the code that you're calculating your statistics with. Maybe you've done some correct operations like 2 + 2 = 5. I don't know. But that's not the type of error that we're going to talk about today. The type of error that we're going to talk about today are statistical errors. And they're also known as type 1 error, which are false positives, and type 2 errors, which are false negatives. And it is important to highlight here that these are errors that they do not have a lot to do with the number crunching, but they have a lot to do with the way that we design studies and the way that we report those studies. So let's start thinking about what those errors would be. The first type of error that we need to think about when we're doing statistics is a type 1 error. And as an illustration, a type 1 error is a fire alarm that goes on when there's no fire. So I have a little picture here to illustrate the fire alarm is going on, there's no fire. Our second type of error that we're going to talk about now is a fire alarm that does not go on when there is a fire, and that could be deadly. But the fire is going on and the alarm remains quiet. Just to start today, I would like everyone to just stop for a second and think, if you had to be cursed with one of these two types of broken fire alarms, which one would you prefer? And if you want to post it on the chat or just turn on your microphone and say something, I would really appreciate. And it's important that we sit and think about this example of the alarm, because later I will try to make connections on how these two malfunctioning alarms, they connect to the statistics that we do and to the way that we report statistics in our papers. So from the audience, does anyone have any gut feeling for the type of alarm that they would prefer? Anita has raised her hand.
Yeah, I know I should feel like the fire is more deadly, but I'm going to be so annoyed by being told something is like a problem and it's not. So yeah, I think the first one's my worst.
Awesome. Gavin.
Can you hear me? Sorry.
Yes, I can.
Yeah. So it would be the one that went off all the time when there was no fire. The type, yeah.
Type 1. Yeah. The one to the left. Thank you, everyone. So I love that, like this is a divisive thing. Everyone has their preferences. Some people would like a fire alarm that goes on all the time, but definitely goes on when there's a fire. Some people do not want to be bothered all the time with a false alarm. I also feel like that in a certain way. But these two concepts, they are very linked to statistical tests. So in statistics, when you get a result that comes back as significant when it's not, the error that you're making is a type 1 error. It's the alarm that goes on when there's no fire. But also sometimes we can miss significant effects in our statistics. And when that happens, we are dealing with a type 2 error, which is the alarm that does not go on when there's a fire. The answer in statistics is that actually we cannot get a perfect alarm in quantitative studies. And that's just the way the cookie crumbles, and there's not a lot that we can do about it. But that when we are designing studies, we usually design them with a trade-off between false positives, the alarm that rings all the time when there's no fire, and false negatives, the alarm that does not ring when there is a fire. The other thing that can happen is that different studies might use a different type of alarm by design, and that's completely fine. You might be designing a study where you do not want false positives at all, but you might be designing a study where actually missing a significant effect could have implications. But what I hope to make clear today is that, number one, it is important for us to communicate very clearly how we have designed our study to look more like the first type of alarm, more like the second, or something in between both. And how this matters in the long run of science is not something that matters too much for one study, but it matters in the long run. And what do I mean by long run? So in statistics, let me try to play this video. Yeah. Let's imagine that this orange curve is the distribution of whatever you are estimating. It might be the grades of your student population. If I play it for a bit, we see one sample coming out of this distribution, and that's your sample that you have sampled your participants from the population. You calculate your mean, which you see as a green dot, and you calculate some uncertainty around the mean, which are the green bars around the green dot. What I mean by the long run is that this point here that we have is the result of one statistical study. But quantitative methods, they are built on the premise that we are going to be repeating those studies forever, or that we might make one study, but we want to have a long run confidence that our results are correct. If you see in here, one of these points now is red, and that means that even though I sampled from my population, my statistics are coming back as a false positive, which is a type 1 type of error. And you should interpret each new point in this visualization as a different study. So that's what we mean by long run. Quantitative work in general is a cumulative effort. So it mostly refers to studies looking at something in several ways, in several contexts. And then in the end, we synthesize all of the studies and we reach some sort of consensus. So let's start now linking a little bit more closely what the type 1 error, the false positive, or in other words, the alarm that goes on when there's no fire means statistically, and how we should report it. So when you're doing statistics, you will normally report something like your alpha criterion, or your confidence interval, and that's usually the significance criterion that you choose for p-values. Alpha can be 0.05, which is some sort of standard, 0.01. This is really field dependent. There is no specific field with unity in it. But the rate at which, in the long run, our fire alarm goes off when there's no fire really represents the alpha that you're reporting in your study and that you're using for design. The other important thing to say here is that alpha is used to construct confidence intervals as well, which are a more explicit way of communicating both the p-value and the uncertainty. We're going to talk about confidence intervals in a little bit. But before I move on, I just want to reiterate that when I talk about error, I'm not talking about a type of error that a student makes in an exam. I'm not talking about a moral failure. I am talking about looking at a number and saying yes or no. That's the error, is what the number represents, yes or no. So it is really about the decision that you make based on your statistics. If you have been with us since the first webinar, please do take a look at the first webinar after you finish this one, because we did talk about type 1 error in the first webinar. And in the first webinar, we were basically contrasting exploratory research and confirmatory research, where exploratory research is the type of research that you might not have a very strong hypothesis formulated, or maybe you build your hypothesis as you do your study, and that means that you cannot control the type 1 error. That's exploratory research with respect to type 1 and type 2 errors. But there's also confirmatory research, where you start your research with a hypothesis that is fixed and never changes, and then your type 1 error is controlled and your type 2 error is controlled. But I think that the true question that we have now is, how can we use these concepts of statistical error to improve reporting? The first one is remembering that there's something such as p-hacking, and that really increases your chance of having a type 1 error. And p-hacking is basically when a researcher, due to degrees of freedom, to the freedom that they have in their research, collects their data, check, is my p-value smaller than 0.05? If it's not, the researcher might do several other things, like collecting more data, excluding outliers, transforming variables, using several tests, or subgrouping differently, iteratively, until significance is reached. The problem with p-hacking is that even though we agree at the start of the research that the probability that our fire alarm is gonna go off when there's no fire is alpha, p-hacking increases that probability in ways that we cannot know. The other practice that we talked about in the first webinar is harking, hypothesizing after the results are known. So that would be more or less collecting data and looking for statistical significance in every section of that data. So when we don't see statistical significance, we don't report it. But if we see it, we report it as if that specific research question were the initial research question to start with, or if that hypothesis were the initial hypothesis to start with. That's also something that we should not do, because it also increases the chance of a false positive, of the alarm going off when there's no fire. So just to recap, we're talking about the type 1 error, the false positives, which one we decide at the design stage of our study, and it is the alpha that we're going to use in any tests that we do. This is pretty much equivalent to the criterion for p-values, that you decide significance or not. But the important thing is that alpha can also be used to construct something that are called confidence intervals. So now we're going to take a look at an example of reporting confidence intervals, and we're going to look at someone reporting the same result in two different ways, but it's the very same result and it is the very same study. Okay, so I will actually mark down 5 minutes for us to quietly read these two examples. Please do read them, because we will come back and try to discuss what these examples mean and how they communicate the probability of a false positive. So I'm marking 5 minutes. I'll just leave us with some quiet reading time. Okay, I'm sorry, I promised 5 minutes, but 2 minutes have passed. I don't know if it's because I drank a lot of coffee, but I've read both of them 3 times. So I'm just hoping that everyone has had a chance to read them at least one. Okay, everyone, so for these two examples that we are showing here on the screen, which one would you find more useful if you were reading the paper? You can talk in the chat. Which one do you prefer? So Luis prefers Tuf, Gavin, João Pedro. Yeah. And there is I'm sorry for the pun, there is a significant difference between these two styles, right? The first style sounds like a robot, you know? They talk about a mean difference, but they don't talk about the p-value exactly. They just say that it's smaller than 0.05. They reject the null hypothesis and conclude that the teaching method had a significant effect on self-efficacy. Sounds very, sounds like very absolute, sounds very binary. But the second one, they actually talk about the difference. They talk about the scale where the difference appeared. They say that in the long run, the confidence interval of their difference is a difference that could be as small as 0.01 and as large as 0.89. And then you see that they are not rejecting or accepting anything. They are saying, this is what my data is telling me. Well, the data are compatible with an increase in self-efficacy. Okay, the data is comparable with an increase. It could be as large as 0.89, but it could be as small as 0.01 points. And that means that even though there is statistical significance, because the first style, the statistical significance is true, it is statistically significant. That statistical significance could mean a large practical difference or a tiny practical difference. And if we imagine that this is a teaching method that takes time, training, resources, expertise to implement, I don't think that I would try to implement it if someone told me from the get-go that the improving my students' self-efficacy could be as small as 0.01. And in here, I'm really trying to tap into the useful part of studies, because the same test that will give you statistical significance will normally also give you the confidence interval. And it is really important for us to report those. So just to give you some more information on the confidence interval, I leave a really good reference here in medical education that really expands the idea in a brilliant way. The confidence intervals, they are constructed based on the probability of a false positive. So if you choose your alpha to be 5% or 0.05, your confidence interval is 95%. If you choose it to be 0.01 or 1%, the confidence interval is 99%. So the confidence interval communicates the uncertainty around your estimate, and it does communicate at the same time the probability of a false positive. As I showed in the little video, this is a long-run confidence. The confidence interval does not mean that 99% of times or 95% of times your mean will be there. The confidence interval means that the quantitative algorithm, the alarm that we are using, the statistical test, has a confidence of 95 or 99% in the long run. And the interesting thing, everyone, is that confidence intervals, they actually demystify the machinery of statistical tests. Pretty much, if you want to test whether an intervention gives you a target improvement like this one here in red, you can simply plot the confidence interval and see, does it cross the target line? If it doesn't cross, it's significantly different. You could plot confidence intervals or calculate them for two groups, group A and group B. If the confidence intervals do not overlap, this would somehow be equivalent to saying that they're significantly different. If they overlap, this would not mean that they are not significantly different. It would mean that we cannot reject the idea that they are the same. And keeping up with my newly established tradition of referring to EJEE work to show some, on the ground, concrete applications of the concepts that I'm talking about. I'm going to talk about this paper here by Sasha Nikolic and co-workers. And basically, they implemented the idea of confidence intervals to extend the type of information that a p-value can give. So they were testing some specific learning outcomes, like, for example, learning outcome C3 for cognitive 3. And a certain group had a confidence interval that was consistently larger than another. You see that the lowest bound of this interval, 3.69, is higher than the upper bound of this other one, 2.96. And they started interpreting that as differences between the groups. So that the confidence intervals, they are a nice way to say, what is the range of conclusions that your data supports, whether two groups or two conditions are different, the data is telling you that, and it gives us that bigger acknowledgement of the uncertainty. So just to summarize what we've talked about, confidence intervals and type 1 error. When we're interpreting results, I can tell this with a lot of certainty. Always focus on your confidence interval. If you have a mean to report, focus on the confidence interval and anchor it on the point estimate. The point estimate is your actual mean that you calculate, and the confidence interval is the interval that you build around this mean. Acknowledge the full range of uncertainty within the CI, the confidence interval. So the confidence interval as in our example, it could be very large. It could go from something that means almost nothing to something that means a lot. And it is important to acknowledge it. One little reminder is that if you have very large samples, the confidence interval might be very short, and you might not need to comment on that. And that is simply because you're getting more accuracy and you're more certain about your estimates. If your confidence interval is long, like going from 0. Let's say 0.1 to, I don't know, 3.2, 3.21, let's say, there's a lot of uncertainty in this confidence interval. You could have a massive, let's say, difference, or you could have an almost negligible difference. So it's always good to temper the conclusions appropriately based on the confidence interval. And I know that this is a summary slide and that I have not mentioned this before, but always report exact p-values. It's just because I don't want to explain the full rationale behind it right now. I'll save it for a next webinar. So for example, instead of saying my p-value is 0.0 smaller than 0.05, we don't do this. We might say that my p-value equals 0.042. Okay? And reporting the exact p-value will help people appraising the literature to synthesize the results of your study. Awesome. So now let's talk about the second type of error that we mentioned today. And that's the deadly silent alarm. And it's the alarm that does not go off when there is a fire. The error, false negative, the error rate of false negatives is normally represented by beta. And beta is the rate at which, in the long run, we're not going to detect a fire when a fire exists. The most important thing is that beta also helps us calculate the power of our study, and I'm going to talk a little bit more about power in a little bit. But I just want to leave this relationship very well explicit here, because I'm gonna just do a quick review of our second webinar, which was our previous webinar. In our last webinar, we were talking about how we use surveys and survey items as a way to measure a construct. So let's say I might be measuring a construct A, as we mentioned here, self-efficacy. Let's say that it's self-efficacy. And then I write 3 survey items that I think capture self-efficacy or that are in the literature. And when we are doing measurements in this way, we are making sure that we measure a construct appropriately through the survey items, and each item will be associated with a type of error. For more details on this, you can go back in the recordings to our second webinar. But the most important thing, I think that the most important message of the second webinar is that we need to look at measurement, validity, and reliability. Because if you're not measuring what you think you are measuring, there is no way that your fire alarm is gonna go off. Maybe your fire alarm is measuring perfume, so it's not gonna go off when there's high levels of carbon dioxide. So it is really important to have reliable and valid metrics for us to start thinking about type 2 error. And the following things that we're going to talk about, they can be applied more or less to survey items, but ideally we're talking about constructs in here, as with surveys. In the last webinar, we gave an example of how surveys are developed, validated, and used. And in this example, we showed that we might have several questions, several items in the survey. And when we do something called an exploratory factor analysis, these items, they group in clusters. And these clusters, they represent the dimensions of measurement. So for example, project planning was representing as a dimension of measurement of interprofessional project management. Project planning was a dimension, risk management, ethical sensitivity, team communication, and interprofessional competence. And then these together, these items, they will give you a number. Let's call it A, B, and C, and D. And these are the numbers really that we focus on to do the statistical tests. So I think that now I might go back a little bit to Tina's question with the next slides. Because one thing is a statistical significance and something else is a practical significance. We already talked about, is method 1 really worth it? Because the improvement that the data in this study found could be as little as 0.01. But we can remember that the results, they were taken in terms of a survey, a self-reported survey where students were marking items, Likert items, reporting their self-efficacy. So we can imagine, can I compare the results of another study with mine? Is self-efficacy something like height? If I measure my height here, if I measure it in Brazil, if I measure it in Croatia, in Ireland, in Sweden, my height is pretty much going to be the same. But is self-efficacy something that travels so well? Does validity of an instrument travel that way? So, for us to start comparing implementations, applications, and between studies, the important thing is that we start talking about effect sizes. An effect size is the magnitude of the difference or association between two groups. For example, here in the picture, you see a yellow curve and a purple curve. When I have an effect size D 0.5, they're somehow different. When D is 1, they're more different. When D is 2, they're even more different. And when D is 3, they're even more different. So the effect size is one of these measures that help you understand how large is large enough and how small is small enough, which I think refers exactly to Tina's question. Because before we were talking about the mean, but now we're talking about effect size, which can be something absolute. For example, if I'm talking about the height, hours of sleep, or maybe even assessment grades, those are pretty meaningful metrics. I have a metric tape to measure height, I have a clock to measure sleep, and those are pretty much the same all around the world. So I can talk about an effect size as the difference between two groups. However, if we're doing things that are more subjective and have more variability in the answers, like self-reported questionnaires and surveys, the ideal thing is to report a standardized effect size. And a standardized effect size pretty much takes into consideration the mean of your data as well as the spread of your data. There's this interesting editorial on the Journal of Medical Education, and they state very categorically that the effect size is the main finding of a scientific study. And they really contrast it to the p-value in saying that it is the effect size and not the p-value that really helps other people build on your research. So now let's see how the effect size can help us avoid type 2 errors, which is the alarm that does not go off when there's a fire. So as I mentioned, the power of your study is the chance that your study is going to capture a significant effect when it exists, or 1 minus the chance that it's not going to capture it. So the main recommendation here is to run a power analysis before even starting your research. And to run a power analysis, we need estimates of effect size. You pretty much need to estimate your effect size. The power analysis is the #1 source of information that will help you determine the sample size that is needed for your study to detect a certain effect size on the long run probability. And in here, I am referring again to our last webinar. When we were talking about quality research questions last time, one of the criteria for a high quality research question is a research question that can be answered. And calculating power helps you understand whether the number of participants that you have access to can help you answer your research question. And with that, you're giving an acknowledgement that type 2 errors can exist. I'm going to give you a practical example. Alex, if you could put in the chat the links for points 2 and 3, that would be really helpful. So let me give you an example. In your context, let's suppose that you have access to 40 participants and that you're running a study with 0.8 power, which is more or less standard, 0.05 significance level, which is more or less standard. But you can choose between 2 experimental designs. One experimental design in the literature, they have identified an effect size of 0.2. In the other experimental design in the literature, they have identified an effect size of 0.5. You can use the data from previous studies in some calculators like this one and like the one that Alex is going to put in the chat in a little bit to calculate what's the sample size that you need to detect the same effect. So if you look at this here, you will see that for the same conditions, when you have a small effect size, it takes a very large sample to replicate. But when you have a large effect size, it takes a smaller sample to replicate, 32. So it is really important to report effect sizes because that will enable people coming after you to design their experiments well. And it is really important to report your effect size because it pretty much takes away the doubt and the question on whether a result is large or small. It pretty much standardizes the difference. And in that world, the question, oh, is 0.89 a big improvement on a scale of 1 to 5 and etc. In that world, those questions, they are measured by a coherent metric like Cohen's d. Keeping up with the tradition of pointing out to practical examples in the EJEE where this type of advice has been implemented, I have this study here, Implementing Serious Games Through a Pedagogical Lens in Engineering Education, an experimental study. And the important thing is that the authors justify their sample size really well. So they use the software G-Power, which I hope is in a link in the chat right now. And with this software, what they do, they use the literature to estimate an effect size that they are aiming to replicate in their study. They use the effect size, the alpha error probability that we talked about today is the false alarm probability, and the power, which is 1 minus beta error probability, to estimate a sample size for each group of 23. And this is the most watertight way to make sure that you don't have disputes on your sample size. So let's summarize what we've seen today. The important thing to remember is that every quantitative study carries error. But what matters is acknowledging that by default, quantitative methodologies are built around the idea of error. and really informing the reader which type of alarm you are using, how are you setting it up, and how are those considerations for error coming into your results. You can use the literature to ensure your study has sufficient power at the design stage. So that's normally power is something that you can absolutely report. I designed my study like this, and that. I looked for the effect size, and I used this calculator, and it told me 23 participants. But it's something that you definitely do at the design stage. You don't do it after you've collected the data, because it doesn't mean a lot. Keeping up with the two examples that we had, report and interpret confidence intervals, not only the p-values and the estimates, but the confidence intervals, they can be interpreted. And always, as that editorial said, some people, especially modern statisticians will really say that the effect size is the main finding of a quantitative study. Always report the effect sizes because of two reasons. It will probably increase your citation potential. People will be able to use your study to power their study, maybe if they're looking at something similar. And it really helps people coming into the future that are summarizing the literature and looking for consensus or the basis of evidence of something. As always, I'll finish with two book recommendations at two levels. The first one is Statistical Power Analysis for the Behavioral Sciences by Jacob Cohen. It is a classic. And this is the same Cohen that identified the Cohen's D effect size. So that's the guy. It's non-technical, so it is really straightforward, and it is a classic. I love my classics. But we also have lots of people looking forward here. And the modern option is Introduction to the New Statistics by Cumming and Colin Jakeman. And this one is for everyone that is interested in open science, in meta-analysis, in evidence synthesis, is for everyone that is looking at the statistics of the future. I am about to finish right in time, and I'm so proud of my timekeeping today. Next up, we have some ideas for the next webinars. We don't have dates yet. However, they will be advertised through the regular channels. We are designing a step-by-step tutorial on exploratory factor analysis and how we can do that, how we can embed the theory, the educational theory on the statistics of exploratory factor analysis. And today I wanted to have shown some tips for visualization for survey and questionnaire studies. But after I put together all of the content, I was like, okay, I would rather take my time into these things. So we will have next up maybe another quick workshop webinar on visualization in survey and questionnaire studies. And also to remind everyone that if there's something that really bothers you, something that you don't know, or something that you would like us to talk about, or something that you would like to collaborate with me in talking about, do get in touch with us. This is a community effort. It's for the community, from the community, and we are implementing this 1 hour format, hopefully so that it's more sustainable, but also that we can have more flexibility.